Hi, in this video, we want to take a look at assessing dimensionality for the purpose of item response theory. All right, so item response theory is concerned with the design, analysis, and scoring of tests, quizzes, questionnaires, things like that. A lot of things that we have specifically for schools, but for other uses also. So item response theory tends to focus a lot on categorical data, a lot of binary data also. And, it's all over the place in schools, school districts, the education world, and, other psychological assessments. So we're going to work through an example. This example is from Modern Psychometrics with R by Mayer. And here's the GitHub page for the code. I went through, I modified the code a little bit, but you'll see that if you take a look at the textbook, you take a look at the code on GitHub, you'll see that I'm being true to it. All right, so what we want to focus on today is thinking about the dimensionality of like a latent variable that's driving the results that we see when we give a test, okay? Or a quiz or questionnaire or something like that. Well, before I can start doing my modeling, I need an idea of like the number of latent variables involved, right? And so we're going to be really looking at kind of like what was very similar to exploratory factor analysis, but we're going to be, being a little bit more specific for the purpose of item response theory. In this example, we're going to be using a neuropsychological test battery for number processing and calculations in children. And we're specifically going to be working with the subtraction columns. So in the data frame, there were 341 students, and there were 18 assessments on there. And we're just going to look at just a few of them, just the ones that correspond to subtraction. I'm going to reduce the output to just 2 digits so we don't get blasted in the face with numbers. And the data set is Zuriki in the MPsychoR package, which this is the package that accompanies the textbook. And to get the actual data that we're going to be using, I'm grabbing only the subtraction columns. So I'm just using grepl to identify which columns have sub tr in the column name. And then we're grabbing those, and that's the only ones I'm going to be working with. All right, so for this purpose, we have 3 major ways to assess dimensionality. First one that we're going to be looking at this quite a bit, is categorical principal component analysis, PRINCALs. All right, so this is the categorical version of principal component analysis, just like the name says. The next one that we're going to consider is exploratory factor analysis, and with the appropriate type of correlations. And then we also have item factor analysis, specifically with like the psych package. So let's go ahead and take a look at PRINCALs. So for PRINCALs, that is categorical principal component analysis, we're going to use the Giphy package, and we use PRINCALs, not surprising there. And I can just go ahead and drop directly my data set straight in. And remember, this is a subset of the entire data set. There's only subtraction involved. And when I do that, we can see our loss value, the number of iterations it took to converge, and the eigenvalues of 2.3 and 1.1. Okay, so remember that when we are dealing with eigenvalues, we generally want them to be above 1. That's one of the criteria. I don't consider that's a very strong criteria. I don't like that criteria personally because it's subject to rescaling. If I was to rescale my data, then my eigenvalues change also. And so I personally do not like the standard of eigenvalues greater than 1, but it's a standard within a lot of fields of analysis. Now, when it comes to iterations, and this is going to come up later also, one thing that is always good to be mindful about is if I have a model and it takes a lot of iterations to converge, that's an indication that my model structure and my data don't match with each other. Here, 33 is super low, so I'm feeling pretty good right now. And just like with principal components, we get our our loadings and corresponding to each variable. Now, what this did by default, it grabbed all the, it took the number of eigenvalues greater than 1, and then it took that number of components. So it took 2. Okay. And then that seems reasonable for right now. We're just digging in, starting to see what's going on. If I wanted to, I would consider decreasing this threshold and start exploring like other components. Now, something about this is that with these methods, the components that we get are not unique. So if I change if I do regular singular value decomposition with numeric data version of principal component analysis, then up to scalars, the direction or the vectors are all the components are going to be distinct and unique every single time. Now, there might be some sign changes, but up to that, I'm going to get the same thing every single time because of the perpendicular aspects. Here, this is not the case. So after we get away from classical numeric principal component analysis, when I start talking about components, if I choose to go with 3 components or 5 components, my first, second, and third may change, and I have to be ready for that. And so if I was like run it with 3, interpret what's going on, then run it with 5, I can actually get different components, and now the interpretation may have changed. So I'll have to go through and reevaluate what's the interpretation of my components. And so here we've got our importance measurements, and these are corresponding to the eigenvalues of the square matrix that's generated by the data. And so we have our variance and our cumulative variance. All right, so now let's go ahead and plot our loadings. Okay, now when I look at this, first thing I look at is the first principal component. It's not principal component, the first component. First component is always going to be the most important one for us to analyze. And I'm looking this way, and I notice that all of them are pointed in the same direction. They're all pointing to the right. Okay, well, if they're all pointing in the same direction, why is that? Well, if I think about it for a second, well, that means that it's kind of like the first component is like overall ability on the test. Okay, that's informative, that's interesting. So if I have a student who has a 1.5 for their component 1, and another student has a -1 for their component 1, then I can be fairly certain that the first one with 1.5 is a much stronger mathematically with subtraction at least. Okay, now what about the second component? The second component, I see that I've got a bunch up here and a bunch down here. All right, how we're going to interpret that is that given a student's relative ability, they're going to be stronger on, so if I have 2 students, let's say that they both have component 1. One is low on component 2, one is high on component 2. If they're high on component 2, that tells me that they're stronger at the topics that are pointed this way, but weaker on the ones that are pointing down. If a student is low down on component 2, then I know that they're stronger on the ones that are pointing downward and weaker on the ones that are pointing upward. So relative for their ability level, it tells me like where are they stronger at in relation to the 2 topics. So the way to think about this, if I had like academic ability, well, that could be like component 1, and then you could have individual subjects. You hear people say, oh, I'm more of an English person than a math person. But when you start talking to them, you realize that they suck at both. They might be better at English, and what they're telling you, so component 1 would be their overall academic ability. Component 2 will be saying for that individual person, are they better at English or math? And in that case, a 0 means that they are equally proficient at the 2. But someone with a stronger component 1 score could be better at both of them. So when we see the arrows pointed like this, all in one direction, that usually is like an overall aspect. And then when they're going in opposite directions, that tells us like a contrast that they're stronger on one aspect given their overall level of ability. Now, the biplot, what this does, this shows us where each individual person is. Okay, so if I look here, let's say I look at 303, and I look at these people here. They have about the same first component. That tells me that the ones that are stacked here and this 303 overall academically are about equally proficient. But this student is better at the ones that are pointed downward than they are at the ones that are pointed up. And these students are better at the ones that are pointed up than the ones that are pointed down. So the biplot gives me information about individual students. And so overall, the students that are strongest are going to be the ones that are farthest to the right. The ones that are weakest are farthest to the left. Now, the scree plot gives me an indication of how many components we should have for our latent variable. Now, a couple of different criterias. One criteria is for us to account for so much variance for all the cumulative components. Another criteria is to get all of the components that have a variance accounted for above a certain threshold. Another one is to make sure that the eigenvalues are greater than or equal to 1, and we can see that that's around 2, maybe 3, something like that. It's hard to really specify with this, but we can see that 4 would be too many by the 1 criteria. Another criteria is to use the elbow method. So with the elbow method, we're looking for diminishing returns. You notice that over here, like there's not much difference between 5, 6, 7, 8. If I keep on going to the right, I'm not getting much more information. The informative value from going from 4 to 8, I really have not picked up a lot, but yeah, I'm going to have a more complicated model. So when I look at this, the elbow method is basically trying to show, hey, where have we hit diminishing returns? I don't want diminishing returns. I'll just stop before I get to that point. So here I can see that 2 kind of looks like an elbow and 4 looks like an elbow. So 2, 3, 4 by this scree plot would be a reasonable choice for the dimensionality of our latent variables. All right, so another option that we have is to use very simple structures and parallel analysis to assess dimensionality. And here we're going to be using the psych package. And so we're just using in factors in the psych package to try and see, hey, what's going on? And so we can see along here what's going on with the first principal component along with the number of factors, and the second principal component, or not principal, the second component, third component, and so on. Every time I say principal, almost always in this video, I'm saying it incorrectly. It's just kind of a reflex because that's the one I use so often at work. Complexity, we can watch and see how the model gets a lot more complex as we increase the number of factors. And so we can see that if I go above 2, I have a pretty big jump in complexity. If I go from 5 to 6, I have another big jump. So if for some reason I was like 5 or 6, how many? I would probably want 5 because I would not be getting that jump in complexity. Now, if I have 3, 4, or 5, I notice that in terms of complexity, I'm not, to go from 3 to 5, I'm not picking up a lot of complexity. So if I was, borderline 3, 4, 5, I might go ahead and go with 5. But here, this is showing that 2 is a good choice because we haven't hit that big jump in complexity yet. And then we have our Bayesian information criterion. Remember that low is good. And then our root mean residual. And here we would like to look for an elbow, but I'm really not seeing much of an elbow business going here. We can see that we've got diminishing returns after 5. And if I go ahead and print it all up, I can go through and individually pick out information about each of the number of factors and get a good idea of what would be the best choice. I can also do a parallel analysis from the psych package. Now here, because of the nature of the data, I have to put in the correlation equal to the poly parameter. Now, what this is going to do is this is going to run through a whole bunch of different ways to assess what's going on. And every time it runs through this, if there's any problems, it's going to start throwing errors. And you'll notice on the screen, there's a whole bunch of warnings coming up. So here, this is just output from it. Since it's just exploratory, this is not my actual model. I don't have to worry about it so much. If I got these warnings after I fit the model, then I'll be like, what's going on with here? But right now, I'm just going to skip all this. There's a lot, huh? And so here, the legend indicates how it's assessing the number of components, and we get our scree plot going on. And so once again, we can see that 2 looks like a very reasonable choice. All right, now if we want to do item factor analysis, here we're going to be using the MERT package, and the big player in that package is the MERT function. So we're going to be calling MERT. I think that's kind of funny, MERT. Okay, so if I want to run things relatively simply, I give it data, I tell it the number of components, and then I'll run it. Now, a bunch of stuff gets spit out with each of the iterations to fit what's going on. So I go ahead and put verbose equal to false. That way, I just don't have a whole bunch of stuff on the page that really is distracting from what's going on. And then we can use summary to run this. Now, something about this in R is a lot of times, if I just run summary on any old object, R will figure out which package to call from to run the summary function. Same for plot, Anova, stuff like that. Here, this is not the case. I actually have to specify the package when I run a MERT summary function. Other packages, if I just run summary without declaring the package, it'll run as is. So that's something to be mindful of. This is true also for like the coefficients, plot, Anova, a bunch of the other standard ones. And so here we can get our loadings, and we get some information about it. And since I only have 1 factor, correlation's meaningless. And let's go ahead and look at the plot. All right, so this looks like a standard probability curve from logistic regression. It's not a probability curve because it's going from 0 to 8, but something that's very, very important. Logistic regression, up, down, left, and right, is all over the place, hidden under the hood in item response theory. So if you're interested in this topic, you really want to stop right now and go learn logistic regression. This is a critical concept to understand how things are fitted and how things are scored and evaluated if you're going to be getting any deeper into item response theory. This will be especially true when we get to the rash models. All right, now let's go ahead and do the same thing, but this time I'm going to use 2 components. Now, I was running through this and I had trouble with convergence. I had to increase the iterations by a lot. I had to go from 500 to 10,000. That's a big increase. So right off the bat, I'm feeling this may not be the best model for what's going on. So for this version, for this way of evaluating what's going on, I feel like 1 is actually the way to go instead of 2. The previous diagnostics we ran have all been pretty consistent, like 2, 3, 4 were good. Now, when I go from 1 to 2, 2 starts giving me problems. And anytime it takes a lot of iterations to converge, like just think, this may not be the best model structure. Now, I haven't seen that written down anywhere, but just time and time again at work, and when I'm working on projects, if it takes a long time to converge, it's usually because the data and the algorithm aren't matching up. The data and the model just are not a good fit for each other. And so it takes a long time to get something to converge. You might want to consider a different structure. All right. And so on this one, you really want to put verbose equal to false because it's going to spit out just tons and tons and tons of output for as it goes through the different iterations. All right. Oh, hey, the light came off and it went back on. There we go. There's an automatic light sensor. I guess I was not moving around enough. So how I control the number of iterations is I take the technical parameter and I pass a list of named parameters. And n cycles is the number of iterations that were applicable for this. So here, when I look at the loadings, we can see the two factors, and we can see that everything is negative. Now, if everything's pointing in the same direction, then everything's kind of like agreeing. So even though it's negative, I'm still reaching the same conclusion in terms of this, the first component is going to be like an overall aspect of the student's ability with subtraction. If I go back up here, I notice that they're all positive, so that this is consistent with everything, the first component, evaluating their overall subtraction ability. And you'll notice if I look through the numbers have changed. That's important. By changing the number of factors from 1 to 2, all of a sudden, my first component loadings have changed, which means the first component has changed. So if I was to go through and analyze the first model's component and reach a conclusion, now I run it with 2, this component may be slightly different. It's probably going to be very similar, but not necessarily. And so if I want to make sure that I have a good understanding of what's going on, I have to reevaluate. My experience is that the first components change the least, second components, the second least, third components, the third least, but the later components, so if I had a lot of components going on and I change the number, those later ones are more prone to changing. And so I need to watch out for that. And here we can see that we got some correlation going on, not a huge amount, but this means that we do not have orthogonal vectors, something to keep in mind. But that's okay for this type of problem, as long as we're okay with it. Now here, remember I've got 2 factors going on. So my logistic regression-ish curve is going to be a lot more complicated. I have an entire plane for those like predictor variables. So now things are a little bit more exotic, a little bit more interesting, and we get a 3D plot. And we can run Anova. Now, when I run Anova on the 2 different models, I see that the AIC, it changed a little bit, but not much. The BIC changes a little bit, but not that much, proportionally speaking. Log likelihood did change, but not that much. And the p-value is not significant. So what this is telling me is that all of that extra work to get 2 components really was not worth it. The first component, at least on this way of measuring, is equally informative as the 2-component model. And so all the extra work of like interpreting and fitting and evaluating that I would do with 2 is not worth it. I should just keep it down to 1. All right, well, that's all I've got for you. Take care and goodbye.